Welcome to my talk called There's More Than One Way to Read Maths. This is going to be an exploration of algebraic literacy, and we're going to focus on the expression 2 add 3 take away 4 add 5. We're going to begin with binary operations. So here are the ones that we see in primary school: addition, subtraction, multiplication and division. Now I want to show them in a slightly different way to normal. Here I've got the operator addition, and I want to show the two inputs to that operator here as the 2 and the 3. We've then got subtraction, which can be represented in this way, multiplication and division, which can be represented in this way, and we can in fact do this for any binary operation. So any function that takes in two inputs, such as these, so the minimum, the maximum, greatest common divisor, or the logical XOR function, all of these take in two values, and there are plenty of others, and we can represent all of them in this way. Okay, what we're going to do next is we're going to evaluate some of these functions. So I've always visualized it as the plus pulls in the 2 and the 3, much like this. Okay, and it evaluates to 5. So we use up the operator, we consume it when we evaluate it. So the subtraction, when we use it, will pull in the values and it evaluates to -1. Multiplication forms 20, and the division will form 3. Okay, and then these extra functions that we've got here, or these extra operators, we have the minimum, which will return the smaller value, the maximum, which will return the larger value, greatest common divisor, which is 2, and then the XOR function, which will return false. Now, if you're not familiar with the logical functions, that's fine. Our main focus today is going to be on arithmetic. Okay, bracketing an expression is hugely important when we're dealing with binary operators. So taking this expression here, we could, if we wanted to, bracket it in this way, where we evaluate the 4 plus 5 first, and then we do 3 take away the result of that calculation, and we get this expression here. So I want to represent it using a tree. We're starting with the 4 plus 5. We're then going to do 3 take away that result, and then we're going to do 2 plus that result. So we end up with this tree that looks much like this. But that's not the only way that we can bracket this expression. We could bracket it in this way here, which would result in this tree. We could also bracket it in this way, which results in this tree. And there's also 2 other ways with 2 other corresponding trees. So for this main expression, 2 plus 3 take away 4 plus 5, there are 5 different ways to bracket it. Okay, let's evaluate some of these then. Okay, so starting with the top left tree, we're going to start with the 4 plus 5 first, so let's evaluate that. We're then going to do 3 take away the 9, well, let's evaluate that, and finally 2 plus -6 gives us a final result of -4. Next tree, we have 3 take away 4 is -1, -1 plus 5 is 4, and 2 plus 4 gives us a result of 6. Okay, so interestingly, we've had 2 different results here. Next tree, let's see what we get. This one turns into -4. Next tree turns into 6, and the next tree also turns into 6. Okay, so we get various results. We either should end up with 6 or -4. BIDMAS. Right, BIDMAS is a parsing instruction. It tells you how to read the expression. I'm sure many of you are familiar with it. We have B, which stands for brackets, I, which stands for indices, which means powers and exponents, things like that, D and M, which stands for divisions and multiplications, and then additions and subtractions. Now, the brackets have to be done depth first, so that means we're starting with the deepest or the most inner bracket that we can find. So if there's a bracket inside a bracket, you start innermost. Then the divisions and multiplications, a rule that's sometimes forgotten is that it has to work left to right. Okay, we evaluate left to right. So this is how I like to write BIDMAS, because it captures the different layers and it shows that we've got the left to right rule there as well. Okay, let's have a look. What does BIDMAS say about our expression then? So we Start with the B, there aren't any brackets, then we move to the I, there are no indices, there's no divisions and multiplications, so all of those are checked off. Right, additions and subtractions. We are supposed to work from left to right, so let's keep track of this. We're starting with the 2 plus 3. Have a quick look at the options there. Those three do not start with 2 plus 3. They all start with different options, so they can't be what BIDMAS is referring to. Then we're supposed to take away 4, which means we've found which one BIDMAS actually wants us to do. So here it is. This is what BIDMAS tells us to do. It tells us to work from the left to the right, do the 2 plus 3 first, then subtract 4, then add 5, and the result is plus 6, okay, positive 6. But what about multiplication? Here we have an analogous calculation. We have 2 multiplied by 3, divided by 4, multiplied by 6. And again, we have these 5 different bracketings with 5 different trees. Each one evaluates to one of 2 options. So 2 of them present with a quarter, and 3 of them give us the result of 9. Well, what does BIDMAS say about this? BIDMAS says that we work through the brackets, there are none, there are no indices, divisions and multiplications, we need to work left to right. So 2 times 3 comes first, then divide by 4, and again we find that there's one option that we're supposed to use, which is this one here. Okay, so let's evaluate BIDMAS. These 2 expressions that we've seen so far, they only have one acceptable bracketing, which means if you were to evaluate them incorrectly, if you were to put the brackets in the wrong place, if you did that mentally or physically, you could potentially end up with the incorrect result. But if you do it correctly, if you use BIDMAS correctly, it does always give you the desired result, as long as you're not trying to apply it to one of these rare ambiguous cases like 6 divided by 2 lots of 1 plus 2. Okay. Now, it does also discard other valid bracketings. So we saw that there were other ways that we could bracket this expression that also worked. It relies on procedural thinking. You give the pupil an expression to evaluate and you say, off you go. They crank the handle and out pops the answer, which is great unless you're problem solving and you need to think in a more agile way. Bonuses for BIDMAS, it is very familiar, it is very widely taught, plenty of resources are available for it. However, it doesn't use algebraic properties. So here is BIDMAS. Here's the very quick summary. Now I appreciate this isn't a full breakdown of BIDMAS and everything that it has to offer. This is only a quick summary because there are 2 other versions that we need to see and compare it to, and if we want to go into more detail, we can do this later on. Okay, our first algebraic property, commutativity. Operations either have this property or they don't. So either they are commutative or they're not. Now, all it means is that you can swap the 2 inputs around. So with addition, 2 plus 3 and 3 plus 2 both evaluate to 5, which means it is commutative. Subtraction, we have 3 take away 4, and if we swap them around, we have 4 take away 3, and they do not evaluate to the same value. Okay, so they are not commutative. Same for multiplication, they are commutative, and division, famously, is also not commutative. Okay, it gives you a different result if you swap the 2 input values around. So, there is a sense in which addition and multiplication are better, they are more valuable to us than subtraction and division, because they have this additional property of being commutative. This means that it would be nice if we could fix them in some sense. So that brings us to inverse normalization. So normalizing is where we take that subtraction that we don't particularly want and we turn it into an addition. And we can do this using a good old rule, which is that subtracting a positive is equivalent to adding a negative. Okay. Similarly, for multiplication and division, we can upgrade a divide sign and we can normalize it into a multiply sign by using the fact that dividing by a value is equivalent to multiplying by its reciprocal. So let's try and fix some of these operators. This subtraction and this division, we want to try and upgrade them to an addition and a multiplication. Well, we can do that by sliding the negative onto the 4. Okay, it's the 4 that's being subtracted. So we now have 3 plus negative 4. Okay, 3 plus negative 4. And we can do the exact same with the divide. We can place the divide on the 2, which results in multiplying by its reciprocal, which is 1/2. Okay, so it's the same as 6 multiplied by 1/2. And this will give us the exact same result. Okay, so these two commutative calculations are equivalent to the original ones. So what does that mean for our original calculation? This 2 plus 3 take away 4 plus 5 should now be normalised like this. We now have 2 plus 3 plus negative 4 plus 5. So let's rebuild all of our different bracketings. Let's have their associated trees and let's evaluate them. Each of these trees now, when we evaluate them, turns into positive 6. Every single one of them. Okay, they all give us the correct result. So this normalizing is very powerful. Not only does one of the bracketings work, but they all work when we normalize. And just to show how much worse this problem can get, if we have 5 values here being added and subtracted together, there are in fact 14 different possible bracketings that we could have, and only one of them is what you get when you apply BIDMAS. Okay, so what do all of the other ones actually evaluate to? Well, here they are. Here are the results. 6 of them give us the same result as BIDMAS. 2 of them give us negative 10, and 6 of them give us positive 2. So we've even got 3 different results this time, and the one that we want is the 0. So what happens if we normalize it? What happens if we get rid of those results, normalize our calculation, and try again? Well, now we have, again, 14 different bracketings, but it doesn't matter which one we use. All of them evaluate to 0. They all give us the desired result. There is no wrong way to do it. This means inverse normalization has some clear advantages over BIDMAS. Every bracketing is now acceptable. It still always gives us the desired result. There's no ambiguity if you absorb the inverses into the main operator. It does, however, require mastery of inverse functions. It allows for agile thinking. Okay, so it's not quite as procedural as BIDMAS is. It's familiar still and widely taught. These are not arbitrary rules that no one's heard of before. These are something we've seen. And there are resources available for these, but it doesn't quite fully utilize algebra yet. So our next algebraic property, associativity. Associativity is this wonderful thing where we've just learnt that the bracketing order does not matter for this expression. So we don't really need this layering of binary operations anymore. We can remove the layering and we can just treat it as one object. Here it becomes a sum. This is the associative property. Okay, bracketing no longer matters because no matter which way you bracket it, it still works the same. They are equivalent. So sums are associative, which means these two calculations are the same. But really for us, that means that we can remove the brackets. Or we can think of it as a single function. It's the sum of 3 values here. And wonderfully, we can also include their inverses. So instead of thinking of it as a new function, we can think of subtracting these values as the sum of the negatives. So what does that mean for our original expression? It means we can think of that calculation as a sum of 2, 3, negative 4, and 5. With multiplication, we can do much the same thing. We can remove the operators and treat it as a single object. It is now a product, okay? Because of the associativity. The bracketing doesn't matter anymore, so it's now one function. Again, the ordering doesn't matter, so the expressions are equivalent. So products are associative. Here is our associative law. It means for us that brackets are not important and we can remove them, and we can think of it as a single function. And again, we can include inverses if you really want to. So that does mean that technically a fraction is a product. A quotient is a product. It's just a product with its inverse. Okay. So what would that mean for this example here? It would mean that 2 times 3 divided by 4 times 6 is just the product of those 4 values there. So we've seen the sum and the product are both associative functions. That uses up the plus, the subtract, the multiply and the divide. But we haven't said anything about any other functions just yet. So here are some indices. We can bracket this in 2 different ways. We can model their trees, we can evaluate them, and we find that we actually end up with different results. So indices are not associative, not in the same way. What about other functions? Well, it's conditional. Some of them, like the lowest common multiple, are associative. Okay, we can break down the lowest common multiple of 3 objects, the lowest common multiple of 2, 3, and 5, into 2 lowest common multiple calculations. You can start with the white part, you can start with the innermost calculation, find the lowest common multiple of 2 and 3, and then with the result of that, find the lowest common multiple of 6, and then 5. And it will still give you the same result. However, functions like the mean, you can't do it. It's not associative. Feel free to calculate it, they don't work out the same. Another one, highest common factor, is associative, and they do work out the same. So if ever you've wondered why you can break that triple calculation into 2 separate calculations, it's because of this associative property. Okay, associativity and commutativity combined. Okay, so we have the sum function which is associative. It's also commutative. That means if we take this sum, we can rearrange its values and we can get an equivalent calculation. So all 3 of these calculations, they do the same job. And that negative sign has moved around. So what's going on there? Well, if you focus on it, you'll notice that it's always attached to the 4. Okay, that negative moves around with the 4. So what we should really do when we're looking at this sum is we should attach the symbols in front of it to the value. Okay, attach the sign to the value. And this is what we like to call a term. It is a signed value. So this expression, 2 plus 3, take away 4 plus 5, should really be thought of as 4 terms that can shuffle around. And this, if we explore it further, takes us into our familiar territory of simplifying terms, collecting terms, like terms, because it's a sign paired with a value. And I've tried to animate this here to give you some idea of how I visualize it, that it's not a static object. These terms are mobile. We can move them around. We can do what we like with them. And as long as you follow the rules of commutativity and associativity, they are yours to play around with. So because products are also associative and commutative, we can take a product, we can shuffle its values around, and we can say much the same thing again in direct analogy to what we've just seen with sums. Take the product, it's built out of factors, and they are a scaling operator like multiply or divide with a value. Okay, so we can treat 2 multiplied by 3 divided by 4 multiplied by 5 as a bunch of factors multiplied together. Now you might want to think of the divide by 4 as an anti-factor. And again, we can have more complex factors if you want them. So that leaves us with 3 different ways of looking at it. We have the usual BIDMAS, we have inverse normalization, which is something we naturally pick up as we go through high school and we look at the different algebraic rules. And then we have what I'm calling SPI, sums, products, indices. These are the structures that we use as professional mathematicians. This is the way that we see expressions. Okay, so it allows us to work with nested structures. They always give us the desired result. it helps us to make the mathematical structure explicit. Okay, terms and factors become objects that we can manipulate and work with. It's not just a procedure that we're following, it is an object to be manipulated. It matches the language that we use, okay? Collecting terms, simplifying terms, cancelling factors, common denominators, all of these things, they are because of the structures that are underlying them. Okay, and there's a new terminology here that I've brought in, which is a variadic function. It's very simply a function that can take in multiple inputs. It makes solving much easier. Unfortunately though, there are not enough resources for this available. Okay, so if I've done my job well today, you'll notice that there are multiple different ways that you could read that first expression. There isn't just one way to read maths. So if all has gone to plan, you should now see that BIDMAS is not the only option. I hope now that you've got an idea of sums, products and indices, if you didn't already have that before, and that you can now see that 2 plus 3 take away 4 plus 5 can be viewed as 4 rearrangeable terms, and this is a very advantageous way to see it. And I hope you've got an awareness of algebraic structure, because this is what is needed for higher level maths, for higher GCSE and for A-level maths. It's really about being able to see the structure that allows you to do the algebraic manipulations that you need. So I only have a little bit more left to share with you on this, which I'm just going to call the encore, because that was the main bulk of the video. But my criticism of SPI Maths is that there's not enough resources for it. I truly believe that this is an excellent way that we can view mathematics, and I'm an active teacher in the UK, so I'm in the process of building a platform for this perspective. Okay, and my goal is to make algebraic literacy more tangible. So this leads me into some of the apps that I've built to help visualize structure. So this here is the tree builder. The whole purpose of it is that a student's task when they're using it is to try to identify the structure. So here we have a sum. We've got to identify how many terms there are. There are 4 terms, and each one of those terms is just a value. There's nothing more complicated going on here. So you can fill in that they're values if you want to, or you can just leave it blank because it defaults to a value. Now we can generate new tasks. It is completely randomized and it will keep giving you more and more random examples. Here we have a product and it has 1, 2, 3, 4, 5 different factors. So we can click product of 5 factors and it will generate the tree for us. Let's have a check. That's all correct. And there we go. Okay, so we can challenge ourselves and go for something a lot more complicated. Here is a much more complicated expression which a competent mathematician will read, no problem at all. They'll identify that it is a sum of 3 terms. So that first term that I've just highlighted, we need to break that down into a product, the right value of which is an indice. The base of that indice is itself a sum. It has 2 terms and the left term within that is a product. Okay, so we can see that this gets much more complicated if you want to tackle a much more complicated expression. Then we can move on to the second term of the main sum, which is a function. Okay, it's a function and it has 1 argument in there. It's just one input. That input is a sum of 2 terms. We have the 7y as the first term, the 9 is the second term, and the left term is also happens to be a product of 2 factors. And then finally the plus 4 on the end is just a value. So we can leave that as is and let's check. There we go, 1 complete structure for the tree. So I've also built an algebraic transformer. So what you can do is you start off with an expression, and here you can see that there is a plus 3, which is a term, and we're given the option to move the term to the other side, or we can distribute the 6 across the linear sum. Okay, so it uses the language that is formal, that is correct and accurate. And if you need to, you can switch it to the binary language, which some of you will be familiar with. Okay, so both versions work. You can either use structural language or binary language, and click the options and it will perform the calculations for you, and it updates the tree, and hopefully that gives people more insight into how this works. So all this work that I've done has led to me having multiple hypotheses about how this could be used in education, and I've put them in a document for anyone that's interested. I will attach it into the description at the end. Okay, so that's there for you if you want to dive in. Thank you very much for watching, and I hope you have a lovely rest of your day.